Now, first, I'll jog your memory by showing you the classwork again. Classwork. This is page 9. Page 9. Part A. To save time, I won't copy the question anymore. Okay? So this is equal to another limit. And then you must divide x. Okay? And then the limit of the function is the function of the limit. So I'll put that in. And obviously, this value is 0. It's a very simple limit. The answer is -5/6. This is the first kind. It's the easiest. You know exactly what to divide. Second, in this question, you must divide x cubed. Choose the higher power to divide. Okay? Now afterwards, you don't have to put the limits in. You already can observe that the denominator is going to be very small. So you say that when x tends to infinity, this value minus this value plus this value simply tends to 0. Therefore, I can say that the limit does not exist. Now, if you're confused about how to present this idea, you can let me know. But the minimum requirement is that for you to realize that, oh, you must be able to tell that this is the case when the limit does not exist. Let me know if you don't understand. Part C. In this question, the denominator is of power 2. The numerator is of power 1. I need to divide x squared. And when I do that, I don't even have to expand the denominator. Limit x tends to -infinity. When I divide x squared, so this becomes 1/x squared. This becomes 2/x. And since I'm dividing x squared, so I'm actually dividing x in this bracket and dividing x in the second bracket. So together it counts as 2 times. So you don't have to expand. Expanding it takes time. Takes time is not wrong, takes time. It's just not necessary. So this technique. Now for the constant, I'll just write 2 instead of limit 2. For this constant 1, I'll just write 1. Okay, in this case, it's 0 minus 0 divided by 2 plus 0 and 1 minus 5 times 0. This is the case when the numerator is 0 and the denominator is 2, and you get 0. You see? Now the difference is that in this question, you get 4 divided by 0. In this question, you get 0 divided by 2. In this case, 0 divided by 2 is an actual answer. In this case, 4 divided by 0 is not a limit that we can accept. Clear?
Miss Chen, I think Eunice is in the waiting room.
One moment. Thank you for letting me know. Wow, so many. So this is the answer for the classwork. Let's move on. Example 8. Find the limit. Now, in this function, you can see that this, when x tends to infinity, the square root x squared plus x also tends to infinity. And in this function, square root x squared plus 1 also tends to infinity. Like I mentioned in the first lesson, we mustn't treat infinity as a number, so this kind of substitution is not allowed. For example, I get infinity minus infinity equals 0. This is just wrong. The answer is wrong as well. To figure out the infinity, to figure out this answer, the limit of this question, we actually need to create a fraction in order to compare. So right now I have this limit. It's difficult to figure out, so I'll create a fraction by multiplying the conjugate. And usually we will multiply the denominator, but this time we're multiplying numerator. So I'm dividing the conjugate as well. Okay. Now, when I do that, I create a fraction. Now I will simplify the numerator only. The numerator is x squared plus x minus x squared plus 1. And I would keep the denominator. It can be further simplified. Okay. And then afterwards, I can analyze the power in the denominator and in the numerator. In the denominator, the power of this function, this is of degree 1. This is also of degree 1. So to summarize, the denominator is of degree 1. The numerator, obviously, is of degree 1. So after I get this idea, then I will divide x. Now, when I divide x, I will get 1 over x. And when I divide x, in this one, I'm actually dividing, let me write more steps. I'm actually dividing root x squared. Also, for the second term, I'm dividing root x squared. So remember that root x squared is still x. So I'm still dividing x in both denominator and the numerator. And then I will simplify. For this one, it becomes 1 plus 1 over x square root. And then for the second one, it's 1 plus 1 over x squared. Okay, so it's a bunch of constant now. Right now, it's a bunch of constant and some function that we surely know what the limits are. So when I put the limit inside, this is when we know surely what the limits are. Now, obviously, right now, at this moment, this is 0, this is 0, and this is 0. And then I can put it in. My final step is to substitute. So my answer is 1 divided by 1 plus 1, 1 over 2. It's a remarkable answer. So if you want to interpret this answer, it means that the first infinity in the original function, the first infinity, it's just 1 over 2 larger than the second infinity. Both of them are infinity, but one is slightly larger. Can you try this technique? Can you try this technique? In the classwork, you will figure out this limit. Next page. When you are done, just show of hand. Let me know the show by giving me the show of hand. Great. Most of you are done. So in this question, in the classwork, I want to show you another way of so-called cheating. Is also a way for you to check your answer with this type of question. So let's say you get an answer and the answer is 1. Okay. Now, how do you know if you're correct? It's certainly worthless if you're going to do all the steps again, because it's difficult for yourself to realize your own mistake. So what you do is that you can pick a rather large number. In this case, I'll pick 100. So I believe that when x is this large, maybe when I substitute inside the original function, it should give me an answer that's very close to my answer. Otherwise, my answer is wrong. So when I put this in, I get 100 squared plus 200 minus 100. And that is okay. And I used my calculator. I just now I did. I use my calculator. I get the answer 0.995. This answer is rather close to 1. So I believe that if I increase the value of x, maybe my answer will get closer and closer to 1. That's how I am more assured the answer 1 is correct. Okay, let me know. Let me know. Look at the extra example. The extra example is the same type of example 8. It's just that we have 2 parts we need to care about. The first part is a something minus something, something minus something. In this case is what do you call it? In this case is a infinity minus infinity. Okay, and also we have another infinity next to it, which is this one, multiplying. A lot of times that the questions are easy. It's just some of you just get too carried away with the expanding. Now I need to show you when not to expand certain brackets. Now here is the bracket that we need not expand. In this question, I have infinity minus infinity times infinity. It's fine with the times infinity. It's the infinity minus infinity we need to change it to fraction. So only this part needs to be changed to fraction. So in my next step, I'm going to multiply the conjugate. Now, how about this? I'll just copy it and leave it there. I will not multiply the conjugate of this either. This, I'll just leave it. And then I'll multiply the same thing in the denominator. Okay. And then when I expand, when I simplify my function, when I simplify the function, I would only simplify this. It's just this multiply this. So that is x plus 1 minus x. Okay. And I'm left with this. You see? And then after the infinity minus infinity, which is the trouble, our trouble, infinity minus infinity. After I change this to infinity divided by infinity, a fraction like that. This is a type. And then I will analyze the degree. This is of degree 1/2. This one also of degree 1/2. And the last term, degree 1/2. So I decide that I will divide the degree 1/2. So when I divide, I will divide root x. And a little bit simplification. Until you feel, oh, this part is very obvious. And then you can do the substitution. Before we also write it in, but you don't have to do that. You don't have to, you can skip that step and write down the substitution directly. So the answer is 1/2. Is it okay? Now we can also check by substituting x equal 1,000 in this case. Maybe I'll figure out 1,001 minus 1,000 times 1,000 and use my calculator to check. Let me do it. You do it too. And it is. It is. Is it fine? So that's all. That's all. Now I'll give you 3 minutes to download the other file in the Google Classroom. If you want to print out, you can print out now. Okay, Loria, can you tell me your class number, please?
7.
Okay, thank you. Now, before we start, I also want to, now this is, if you look at the title, we're going to learn another limit, right? Now, it's like when we design the course, we first talk about what is limit, and then we go to find different limit. Now, if you did pay attention, but it was not said explicitly in the textbook. But if you paid attention, you should realize that in the first 2 lessons, we found limits of rational function and irrational function. Yeah. Think about it. Didn't we simplify a lot of fractions? Those are rational functions. And also simplify some of the square root functions. Those are irrational functions. Now, so in M2, you will find that a lot of topics we're going to study a certain concept, and then by like different kinds of functions, just one by one. Now here we arrive here, and this is one of the trigonometric functions. So we will learn this special limit, what I call a special trigonometric limit. And then we will find limits that are related to trigonometric functions. Okay? So here, what is the most important thing in the trigonometric functions is this special limit. When we realize that the angle, which is theta, the angle, and the ratio of the angle which is the sine ratio, are actually very close to each other when the angle is very small. Now look here. Look here. So we will test if they are really very close. So take out your calculator and first change the unit from degree to radian. Now you can think about why we need radian. Now because you can see that this fraction, right? This sine value is a ratio. Now degree is not a ratio. A degree is 30 degree, 90 degree. It's a way we define how large the angle is. But the radian is a ratio. Now a radian is defined as the arc length divided by the radius. So that is a ratio as well. So in fact, we're comparing a ratio to another ratio. So this very important thing is that you realize here x is equal to some radian. So these values are all radian. So change on your calculator, change the degree to radian. And then input sine negative 0.5 radian. You should get negative 0.4794. I can just imagine some of you did the calculator part. And then when I divide sine x with x, I should get 0.9589. Second step, when I input sine negative 0.1 radian, I get negative 0.0998. Correct to 366. And then when I put the ratio, it's 0.9983. Next, I get negative 0.0100, and then Divided by that, I get 1.0000. And the next one is even more ridiculous. It's negative 0.0010, and then I get 1.0000. So you can see very quickly. Now, when the angle is quite small, to be honest, quite small. When the angle is negative 0.1 radian, which is smaller than 1 degree, right? I think so. 1 radian is about 57 degrees. So 0.001 radian is about 0.05 degrees. Yes. Okay. So you can see the ratio very close to 1. Now with the positive number as well. So I'll just copy the answer because only the negative sign is changed. So 0.4794, 0.9589. This one you can still see a little bit difference. And when it gets smaller, and then when it gets smaller, now this is when I correct. I kept 5 6 it's very close. So by studying with evidence, we conclude that this is a special limit, and the limit is 1. Okay. In the textbook, in the appendix, you can see the so-called proof of this limit. This is a geometric proof. Now, when I was your age, I also learned this proof. I suppose it's quite interesting to look at. Is it fine? So I will use the geometric meaning of x, which is the ratio, sine x, which is the ratio, and tangent x, which is also the ratio, to actually deduce, geometrically deduce that this limit is 1. It's a new thing. That's a new thing. It's not part of the syllabus. You will not be required to solve a problem similar to this, but it's like it's something that you need to learn from math. So the geometric proof of this limit. So first, let's understand what x is. So x here is an angle. It's also equal to the arc length divided by the radius. So here, if my radius is 1, so this is a big circle. There's a circle, and the radius is 1. And my angle is x, which means my arc length is also x. Agree? Okay, so arc length divided by the radius equal to the angle. So the blue line, the length is x. Second, let's look at the meaning of sine. Sine x equals to the opposite divided by the hypotenuse. In this case, the hypotenuse is 1. So in this triangle, I call it ACE. ACE. So ACE, CE divided by 1 is equal to sine x. So CE equals sine x. So geometrically, sine x equals CE. Similarly, in triangle ABD, focus on ABD. Focus on ABD. BD divided by 1, which is AB. BD divided by 1 is equal to tangent x. So that is why BD equals to tangent x geometrically. Is it fine? Let me write it down. In sector AB, BC. BC, arc BC divided by AB equals to the angle X. Therefore, BC equal X. In triangle ACE, CE divided by AC equals sine X. Therefore, CE, the straight line, the line segment equals sine X. In triangle ABD, BD divided by AB equal tangent X. Therefore, BD equal tangent X. Now, let's do something. So, we know that from the geometric figure, we know that the area of triangle ABC, sorry, it's not ABC, ACE, is smaller than sector ABC and smaller than area of triangle ABD. Right? ACE is smaller than ABC, smaller than ABD. Okay? Now, when I express them, the first triangle, sorry, not ABE. I made a mistake. Not AB. ABC. Triangle ABC. Triangle ABC smaller than sector ABC, smaller than triangle ABD. Okay? Still hold, still hold. Let me repeat. ABC smaller than sector ABC, smaller than triangle ABD. The area of ABC is 1/2 times base, which is 1, and times height, which is sine X. The sector of ABC is equal to pi r squared times the angle ratio. Now, usually we will use theta divided by 360, but here we cannot. We must use x divided by 2 pi. As here, the angle at the center is x, and the whole circle is 2 pi. 2 pi meaning 360. So here I must use the radian divided by the radian. That is the ratio of the sector. Okay? And for the last triangle, the largest, it's 1/2 times the base, which is 1, times height, which is tangent X. Now this inequality must be simplified. 2 sine X over 2 smaller than X over 2 and smaller than tangent X over 2. To further simplify, I get sine X smaller than X, smaller than, here tangent X, I also change it to sine X over cosine X. Okay, now I'm going to divide sine X. So 1 is smaller than X divided by sine X. Now here sine X is positive. Okay, the geometric meaning of sine X is positive. So I do not change the sign. So I get this. So now I know that this is a constant 1. A constant. This one, the limit when x is very small of cosine. It's a trigonometric function, but also a continuous function where x equals to 1 can be just satisfied into this function. Remember that in the first lesson, we discussed the easiest limit that you can look for. That is the limit on the continuous function, and we can just find it by substitution. And cosine 0, it looks suspicious, but cosine 0 is actually 1. So in this case, 1. So what conclusion do I have? This value lies between a constant 1 and another value which is going to get to 1. Now, this value is going to be 1 in the future. It's not 1 yet, but we'll get very close to 1. So between these two very close values, the limit of this function in the middle can only be 1. That's why this proof is also called a squeeze. Do you know how? It actually makes sense the calling it a squeeze, because it's two sides putting them together. It's like one side is bounded and the other one gets closer and closer. And this function, I don't know how it changes, but it has to fit in between these two so that the limit must be the limit of the function in the middle must be equal to 1. Okay, so we will say that in this conclusion, we will say that send x to 0, and then we get the limit of x tends to 0, x divided by sine x equal 1, and also the other way is also correct. Okay, so beside this special limit, we also have this equivalent special. I cannot say which one is more special. They are just the same. Sine x over x, they're very close. And x divided by sine x also equal 1. Example 9. Now this one you have to learn how to apply. It's not just the proof. It's just for maybe to broaden my math knowledge. But this example 9, you actually need to learn the technique. So how do I find these limits? Now, when you look at them, you can see they are trigonometric functions, right? How do I find the limit? Now, this one, A. This limit obviously cannot be obtained by substitution. When you put x equals 0, the denominator is 0, cannot be undefined. So no substitution. So I need to use the special limit. How do I do that? I will change sine 3x divided by 3x. Instead of dividing x, I'm changing it to divide by 3x. And then I'm going to multiply 3. Okay? And after that, I'm going to take 3 out and only write this limit. In this case, I can, you know what I mean? 3x can be seen as an angle that close to 0. So this limit is a special limit 1. So the answer is 3. Is it fine? I hope so. Let me know. Part B. Limit x equals 0. Tangent x divided by x. This case, we always prefer sine over tangent. So I will change tangent to sine over cosine. And then divided by x, I'll multiply 1 over x. And then I'll do some rearrangement. I'll put sine x and x together and 1 over cosine x somewhere else. Now I can split them into two limits. One special limit, one simple limit. The special limit equals to 1, and the simple limit can be found by substitution. Now here you don't have to write degree sign because we're not doing degrees. This is 0 radian, okay? So this is 1 times 1 equal 1. Any question? Just shout out. Shout out. Part C. Limit x tends to 0, sine 5x, sine 2x. In this case, I will write sine 5x here separately with sine 2x here separately. And then I'm going to write another fraction line because I know I will need them. Now here, I will write 5x because I need to create this special limit. Now, when I multiply here, I should also multiply here just to balance it out. And also similarly, I'll write 2x here, and then to balance it out, I'll write 2x here. Okay? In this case, I will have 3 parts. The first one is a special limit. The second one is a special limit. The last one is a constant. So the answer is equal to 1 times 1 times 5 over 2. The answer is 5 over 2. Any question? Finish the classwork on the next page and let me know when you're done. By show of hands. Okay, maybe part A. It's a little bit different because there's a fraction. With a fraction, you need to divide 3 in the denominator and multiply 3 in the denominator. Let me repeat. This is how you balance it out. You divide 3 in the denominator and multiply 3 in the denominator. Okay? Now, in the previous question, it's to divide 3 and multiply 3. Divide 3, multiply 3. This one is divide 3 in the denominator and multiply 3 in the denominator, which is divide 3. Okay? The second question, the answer is 1/2. The last question, the answer is 3/7. Again, these answers can all be checked by a substitution with a very small angle. Remember, it's an angle. You need to input x equals 0.1 degree, maybe. Oh, sorry. You need to substitute x equal 0.1 radian. But the rest of the questions are similar. It's just that the function is more complicated and we need to use some of the identities we learned last year. And don't worry, I typed out the ones that you're going to use tonight. Mainly there are 2. Okay? So for this one, remember our special function, our special limit is only about sine. So whenever you see 1 minus cosine, it has to be changed to sine. Okay? And there are many ways to change cosine to sine. One of them is known as the double angle formula. So the double angle formula today, you don't have to just to study all the identities again. Tonight, just the double angle formula, okay? Just this one. So for this question, I don't want to write the question again, so I just say equal here. So I'll keep this one and change cosine to 1 minus twice sine half angle squared. Now, it's not entirely the same. In the formula, it's double angle to a single angle. Here, I change a single angle to a half angle. Okay, and then to simplify. Now, when simplify, I'll take out 2. I'll also write the square this way. Okay. And then we know that because the limit can be put anywhere inside the function, so I'm actually going to take limit inside the square. Okay. So before it was the limit of the function squared. Now it's the square of the limit of the function. Am I saying it right? I think so. In this step, it's the limit of the square of the function. In this step, is the square of the limit of the function. Now, I need to use my special limit. By doing that, I need to keep this angle, and then I will divide 2 in the denominator and multiply 2 in the denominator. Okay? So the answer is 2 times 1 times 1/2 whole square The answer is 1/2. Okay, as long as you change cosine to sine, then you're fine. Okay, so now for part B, it's similar. Now, when you have cosine minus cosine, you also change it to sine. Now, how do I do that? It's through this sum to product formula. It's very rare we need to use this. This, I think, in our curriculum, there are only 3 places we need to use the sum to product formula, and this is being one of them. And it's very, I think we'll show you so many times you will never forget. Okay, so this part you definitely need to use the sum to product because that will give you sine and sine. In this case, it's -2 sine. I'll just get the answer. It's 3 plus 1 divided by 2, which is 2x. And also the other one is 3 minus 1 divided by 2, which is x. Okay, and after that, everything is easy. I'll take out -2. I'll change it to sine 2x divided by x and sine x divided by x. In order to use the special limit, I will divide 2 here and multiply 2 here. In my next step, I will take out this 2 as well, so -4. And I have 2 special limits. Sine 2x over 2x, and then sine x over x. So the answer is -4 times 1 times 1. That's -4. Okay. Any question? Do you want to skip any steps? Let me know which steps you want to skip. I'll give you a final verdict whether or not it's allowed. Now, you will do the classwork after I explain 2 more examples. Next page. Still similar. Similar, and I don't know why I put it there, but I think it's more complicated. Also, there are some ideas I want to further elaborate. Hey, let me copy the question. Now, this question, I think to most of people, expanding will be the first step to do. But for me, no. Now, I also want to explain to you that you need to grow an I for functions that are good. Now, here I spot out that this function is good. So I will put it out, and then I will deal with this separately. So in my mind, I already call this function good. Why do I call it good? Why are the other 2 bad? The first function is good is because I realize that it can be done by simple substitution. Now, this is not a very strange value. 1 plus cosine 0 is just 2. Okay, so it's a good function. You don't have to mix it with the other ones that are bad. Now these two are bad because both of them are 0. Now 1 minus cosine 0 is 0. X squared is also 0. Now in this case, I will simplify these two. This one, again, I'll use the double angle formula. And then I will get right? And then I will get and then the answer. Okay. Now I suppose expanding should also work, right? Expanding, you just get a square and it's not that difficult. But okay. Sorry, made a mistake. I forgot there is a coefficient 2. I didn't write. The coefficient 2. So it's 2. So 2. So the answer is 4. Please change it. Let's change. In the double angle formula, there is a coefficient 2 in front of the sine square. Okay. Now I was talking about if you actually did the expansion, you can still solve it, but maybe for some other questions, you will increase the difficulty without knowing. So I suggest that if you can spot the good function inside the mixture of this, then you should take them out and do the substitution. Okay? And then you only deal with the part that are bad. Part B. Now part B is just a new type where the mixture of several techniques are used in this question. Part B. Limit x to 0, sine 3x minus sine x divided by 5x plus sine 4x. Now this one, with the numerator, it's sine minus sine. You mustn't change it to, or should you? Now you can try change it to some from sum to product, but I already know it will not work. Because of the, not because of the sine minus sine, it's because of the 5x plus sine 4x cannot be factorized easily like that. Okay, although we know how to deal with the sine minus sine, the denominator is mixture of a polynomial and trigonometry. So it's difficult to manipulate. So for this question, when you see it, you must realize this is what you do. That is to divide x. We very seldom do that, but in this case, we must. That is sine 3x divided by x minus sine x divided by x and 5 plus sine 4x divided by x. Okay. And in my next step, I can find each limit. 1, 2, 3, 3 of them, each limit. Because the first one will be sine 3x divided by 3x multiply 3. The second one is a special one. And the third one, I can get it by divided by 4x and multiply 4. So for this one, oh, I don't need to write this again. Now I know that this is 1 times 3 minus 1 and 5 plus 1 times 4. So the answer is 2/9. Okay. I think only for this one. This is just very special. Very special. For the rest, I think I cannot say for all because each question is slightly variation. But this is the general idea how you solve it. Can you solve the classwork and let me know when you're done? You should be able to finish now, right? Now let me know if you need any help. Now, the answer to these two questions are -8 and 9. If you have any problem, you can stay after the lesson, otherwise you can leave.
Miss Chen,